Dun, 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 dun. This video is completely extra, meaning you are not required to know anything for this video, and if you'd like to skip it, you are welcome to skip it. Just click next now. Those of you who are still watching it, the purpose is to talk about how the equation for the standard deviation came to be. I remember when I took my first stat class, I raised my hand and asked the professor, why is it that we square it? Why is it that we have n minus 1? And his response was, I don't know. And I thought, so my goal here is to show that there is a good reason for this equation and to explain why. Some of it's mathematical, some of it's intuitive. Let's start with some of the math. If you want to see a normal distribution on your calculator, this function, e to the negative x squared, is what you type in and it'd do a normal. Now, it won't do a normal the right size, shape, or location for what you want, but the full equation is a little confusing. And this will suit our needs for what we would need in an introductory class. So this represents probability for a data point. If we had lots of data points, then we would take the probability for each one, multiply them together, which ends up looking a lot like what we started with, except all those squared values are now added up. Do you need to know what E is and how to do these equations? No. The point I'm trying to make is that the normal distribution uses an x squared in its exponent, and so we add x squared things together if we're talking about lots of normal things. And in our case, what we're interested in is how far away is each of these data points from the center, the balancing point, the mean. Here's my x bar, it's the balancing point. The distance from this guy to the mean, that's called his deviation. We want some way to measure that deviation across all these guys. This data point has his own deviation. This data point has a different deviation. If we want to combine those and we want to use it to talk about the normal distribution, that's when we want to do the squaring. If we weren't interested in the normal distribution, if we wanted to talk about the Poisson distribution, then we would do something different, like absolute values. And we could do xi minus x bar in absolute values and add it up. But that would apply to a different distribution and it wouldn't be as useful for the normal distribution that we're using. There's one called the median absolute deviation, which is actually pretty common and useful for a lot of scenarios. So if you were thinking of some sort of absolute value or average of absolute values, there's nothing wrong with you. It's just there's some mathematical tricks that are helpful for the normal distribution that you would be missing with those. Now, why do we divide by n minus 1? If you were thinking you wanted to divide by n, it does exist if you know mu. With mu in here, dividing by n would be the right thing to do. The problem is a lot of the scenarios we're going to work with, especially later on in this course, we don't know mu, but we can calculate x bar from the data. Now this guy we are not going to use in this class. I'm only showing it in this video so that if you thought this made sense, I'm telling you you're not stupid. It makes sense, but that's if you know mu. If you didn't know mu, you've lost something. You've lost a certain amount of accuracy. When you try to estimate the standard deviation, instead of using the true value for mu, how much information have you lost? And it turns out that if you're using mu to estimate the data, and then you lose mu and instead you use x bar, you've lost as much information as if you lost an entire data point. So it's n minus 1 data points because we've lost accuracy thanks to using x bar. Another way to think about this is we're trying to estimate how spread out this data is away from mu. And if we knew mu, that would give us a very clear picture. But now we're picking an x bar, which is forced to be in the middle of the data set. And so it's going to look like the data is more clumped together because x bar is right in the middle of where it should be. So you're going to estimate s as being a little too small. How do we fix that? Well, let's divide it by less than the n, and that way our estimate will increase a little bit to account for this uncertainty. Another way to figure out how much should be subtracted is to ask the question, if I knew the true mu, how many of my data points were really random? Well, these guys were all random except for the last one. If I told you all the numbers in the data set and I told you the average, but I didn't tell you the last data point, you could calculate what that last one would be based on what the average was. It'd be a lot of math and it'd be a pain, but that means that n minus 1 of these are random given the mu. Now, if we were in a theory class, we wouldn't just say it makes sense intuitively. We'd actually do the math, we'd use calculus to do a log derivative, which gives us the maximum, and say, there is the best equation. But it has mu. And if we just blindly replace mu by x bar and then take an average, we expect to get not quite sigma squared the way we want it. We'll actually get an n minus 1 over n, which then tells us replacing the n with an n minus 1 gives us a valid estimate for sigma squared. But that's math nobody really wants to see. So when I say we need to subtract by something smaller in the denominator, just believe me that subtracting 1 is the right number to be using. Now all of this is designed to get a good estimate of s squared, not s. And there's mathematical reasons for that. S is much trickier to work with. But why do we change s squared into just s? An easy answer has to do with units. If each of these was inches that we were measuring, then when we take the inches and we square it, this is in units of inches squared. What does that mean? Feet squared, pounds squared. That's not the way I like to think. So if we square root our result, this goes back to the original units we had, which would be just inches, and then we can think about what this means in the context of the problem. With the picture of the normal distribution, it's even more strong what it means. There's a spot on the curve where it stops curving downwards and starts curving back out. Calculus would call that an inflection point. But this spot out to the mean, that is a standard deviation. So it shows up nicely on our graph, and when we talk about the normal distribution, you'll see me draw this lots and lots, and that is our standard deviation, and this is the best way to estimate it.